Hello, everybody. So now we're going to start the discussion on the equations that we use to describe the fluid flow, the differential fluid flow. And the equations that we are going to use are the same equations or fall under the same categories that we used before, which are the conservation of mass and the conservation of energy or momentum. Both are different forms of the same equation, which is the Newton's law, which is the conservation of energy law. What we used to do before is that we used to use the same equations, but for simple cases. We used to deal with incompressible flow for steady flow, and we didn't care about the differential flow. We just cared about the flow as a whole. And this is why the equations that we used were simple and they were algebraic equations. Now we are going to deal with the differential analysis of the flow. That's why the equations will be more complicated or more detailed. But the equations are going to be the same categories, the conservation of mass and momentum. So it's not going to be something different from before from the concept, but the shape of the equations will be different. Now the first equation that we're going to use, which is the conservation of mass, which we call the continuity equation. It's we already did the derivation for this equation before in chapter 5, and we reached this form of the equation. And if you remember, we spent some time to discuss the equation and understand what the terms mean, and we said that the first term here represents the accumulation of the mass, and this term represents the mass out minus mass in. And we said that both are included in only one term because of this dot product, which will have positive or negative values depending on the direction of the flow. So we said this n is the normal vector to the surface outward towards the outside the control volume, and the dot product would be positive if the velocity has the same direction of this normal vector. So if the flow is out, then the dot product is positive. If the flow is in, then the direction of the velocity is opposite to the direction of the normal vector, so this dot product would be negative. So this is both the outlet flow minus the inlet flow. So this equation is the accumulation minus plus the output minus the input is 0, which is the general form of the any conservation of mass equation. So we also said that we don't like to have the integral with respect to volume and the integral with respect to area in the same equation. That's why we can apply the divergence theorem, which will convert the u dot n dA into del u dV. And we will also include the density here. So now we have the integral, the two integrals are both with respect to volume, so we can add them in the same equation, or in the same term, I'm sorry. So this is the form that we will have after applying the divergence theorem. Now this is an integral equation, and we can simplify it by getting rid of the integral by differentiating both sides with respect to volume. So differentiation of 0 is 0, and the differentiation of the integral is what is inside. So this is what we will have at the end, which is the more simpler form of the continuity equation, that the shape that we have here, and it's a general form that applies for compressible and incompressible flow, for steady and unsteady flow, and it's kind of a very general equation. Now this equation can be applied for simpler cases, meaning that there are some special cases if the flow is steady but it's still compressible. So if it's steady, then the time change or the density change with time is going to be 0, and the equation will reduce to the second term only. And if it's steady and incompressible, then the density is constant, so we can get the density out of this differential. And now we can write the equation as del dot u. So it's even more simpler now. it's also important to remember that this is three equations. It's not only one. This is equation that has a component in x, y, and z, or r theta and phi, or whatever the coordinate system we use. So it's still a three component equation. So this is the continuity equation. Now we are going, or next video inshallah, we are going to discuss the conservation of energy or the linear momentum equation. So we'll see you then inshallah.